Voilà, after security, fairness again. So let me quickly start with a short recap of what we saw last time. And so last time I started with motivation, why fairness matters, how does it occur that some models may not be fair. And we saw an example of label bias, so where the labels do not exactly represent the target that we actually want to predict. The example there was the healthcare example, where we used the health cost as a proxy instead of the health situation of a patient. And we saw that this proxy of the label was actually correlated, or the errors that were in this label were correlated with the ethnicity of a person, and because of that, and black people were less likely to be assigned the label that they might need additional care in future. So that was one example. Another example was maybe more related to selection bias. So where the recruitment example of Amazon, where the algorithm learned that IT jobs were mainly executed by males. Then there was also this small digression when we went to the scanning of the CVs, and that language models still have a lot of bias in them. They also learn about the gender of words. So if you have a CV, even if you take out the gender of the person, the name of the person, still you can derive by the schools they went to or the hobbies they have and the gender of the person. This gender has signal. Some jobs are mainly executed by males, some by females, and the system learned that and made predictions in that way. You could say this is like a little bit on the edge, maybe. There is a selection bias, maybe also self-selection bias, that some people do not apply for jobs because they think they will not be able to get the job, or people are not selected, not invited for the job because the recruiters think that these jobs are more suitable for certain genders. Or you could also say, if you look in employment, very often you have this situation that, again, the label does not exactly represent the target that you want to predict. Because it's not because most teachers are women that when people come to you, your recruitment agency, or an employment agency of the government, let's say, that you should offer teacher jobs only to women. And then you basically want to offer it both to males and females. And because of that, the data does not exactly represent the label in the data. What jobs are people doing does not exactly represent what you want to predict and what jobs do I want to offer to people. Another example we saw in the previous lecture, where the lecturer talked about self-selection bias. The surveys that were sent to 10,000 people, and then only very few people respond to the survey, and these are probably people that are already interested in the topics or more aware of the topic or more positive towards the topic of the survey. Also, in order to predict the outcome of elections, it's very well known if you take internet surveys, people that are more reachable through the internet or through certain channels, and that there is a certain bias towards certain parts of the population. And so if you use that to predict the outcome of the elections, then you may get a biased prediction. So many of these things occur in a very natural way and without having the intention to discriminate, and often we're unaware of it. So that was the second topic then, measuring bias. We want to measure how fair our models are, such that if our measure tells us, okay, something is wrong, that we can intervene. So there we basically saw three group fairness measures. There are many, many more, but all of them have a similar flavor. And I understand that it's sometimes very confusing which one is what, so I always try to repeat very quickly if we are comparing different measures. But the first measure was basically where we have some affirmative action. And so even though our data doesn't tell us that two communities have the same probability of the positive label, we want our predictions to have this property. For instance, teachers are mostly female, at least that's in Belgium. I don't know how it is in Estonia. So our data, if you look at what jobs are people doing, we will see that there is a bias towards females for teacher jobs. But we do not want, if we make recommendations of this is a suitable job for you. We want to be offered 50-50 to males and females. So if you're male or female, the probability of being offered the teacher job has an equal probability, or be recommended this job. So that is statistical parity, and that's connected to affirmative action. That's the first measure that we had. The second one came from this COMPASS case. The COMPASS case where we predict if someone will recommit a crime in a later stage. And there we saw that the errors that were made for black and white people in this example was very different by the system. If you were black, it was much more likely to predict that you would recommit a crime if you wouldn't. So if you restrict all those people that did not recommit a crime, it was more likely to make that kind of error, a false positive. And for white people, it was much more likely to make the other type of error, the false negatives. So that was the second measure, then equal odds measures. So we want people to have the same odds, the same probability of errors. Well, of course, we want that no errors are made, but if errors are made, we want them to be made in the same proportion and the same kind of errors for both communities. That was the second. And then the third one was calibration. There we basically say, okay, if I tell you that you are high risk, and my predictor, my model tells that you are high risk, then the interpretation, what does it mean high risk, should not depend on your ethnicity or your gender, whatever is your sensitive attribute. So it means, for instance, high risk, 80% probability for recidivism. So the probability that of your true label, given the predicted label, should not depend on the sensitive attribute. Like these last two, they seem very similar, but they're not entirely similar. I showed that with this picture of these people, and then they could be divided in different ways, and depending on how you looked at it, it made a difference. So then we stopped last time by looking at, okay, so now we have different definitions. So what will we require for a model? When will we call it fair? So there are three different ways of looking at it. That's not very convenient. Should we pick one of them, or should we require all three of them to be satisfied at the same time? Well, and this second thing does turn out not to be an option. We already saw for the first two that they could not be combined. And so if I say, and so I have in my data set, teachers are mainly female, and I want my model to make predictions where males and females are recommended the teacher job in an equal fraction, the only way that I can achieve that is by making errors in different ways for the two communities. And that's actually very logical, right? So we have this, what is in our data set. You're female, then there is, let's say, 20% probability that you're a teacher. You're male, it's 10%. And now in my prediction, I want it to be both of them like 15%, or both of them to be 10%, or both of them to be 20%. So the type of errors that I will have to make are different. And like if I go this 10% of the males, I want to go to 15%. It means that for 5% of those that are not teachers, I need to predict that they might be teachers, that teacher is a good job for them. And for the females, if I want to decrease, that I need to 5% of teachers, and then to predict that they teaching job is not suitable for them. So the errors that I need to make are different. In this case, it's a false positive, predicting that someone is a teacher while he is not. And in this case, it's false negative. And we saw mathematically, we cannot combine them. Very logical if you think about it, okay? And so our data set has inequality, and we want our predictions to be equal. Then, of course, we will need to diverge from original data in different ways, making different errors with our original data set. Voila. So now we have reached the point where I can pick up for today. We will also see that for the other two measures, the calibration and the equal odds, that also they cannot be combined. So those were the two in the COMPASS case. And so where ProPublica, the investigative journalist, said, okay, this system is very discriminatory because the type of errors that are being made are very different. And then the company defended themselves, no, our classifier is calibrated. If we say high risk, it doesn't matter what is your ethnicity, it means exactly the same thing. So this is very problematic because it means that you as a developer, as a data scientist, if you will make a model and you cannot combine these two measures, then if you satisfy the first measure, then people can attack you with the second measure and the other way around. So maybe we should try to combine both of them, but again, this turns out not to be possible. Voila, so again, the definition, but I think it's probably more clear with an example of a confusion matrix. So we have, this is an illustration of calibrated, so how to interpret this image. So the pluses and the minuses represent the true labels. And so we have learned a model on a training set, and now we have a validation set, and we want to measure the fairness of our algorithm on our validation set. For the validation set, we know if these people recommitted the crime or not. We also know the label that was assigned by our model. And so we have our two communities, and black and white here. So we have our predictions, low risk, high risk, and then whether they recommitted the crime or not, plus or minus. So we see in the low risk group, 1/3 of the labels is positive, so 1/3 are errors there. In the high risk group, 2/3 are errors. This model is calibrated because if I tell you low risk, it doesn't matter whether you're black or white. In both cases, it's 1/3 that committed a crime again. In the high risk category, it's also equal between the two communities. And so there we compare top and bottom. So this is calibration, and this was the defense of the company. And when we look at equal opportunity, we see that it does not satisfy equal opportunity. Equal opportunity has to do with the errors that are being made. So then we do not look, so then we look at the two communities separately, and then for the blacks, we see that there are 5 positive ones. And for those positive ones, for 4 out of 5, it's predicted that they are high risk. So this is the probability of a true positive, and they are in reality positive, and we predict them to be positive. For the white people at the bottom, there we see there are 4 of them, and 2 of them are predicted to be high risk. So there are 4 pluses, and 2 of them are really in a high risk. So the probability of a true positive is 50%. And then you have these false negatives that are and the complement of that, which is 1/5 and a half. So the errors that are being made are not the same in both groups. And similarly, we have for the other type of error, and for those who are not criminals, well, they at least just a one-time criminal, let's say, they do not recommit a crime. Then we see that for half of them, it's predicted to be high risk anyway for the black people, and only 1 out of 5 for the white people. And so this is, again, an illustration of what we saw before, and that we can be fair with respect to one measure and unfair with respect to the other measure. Now what we see here, and in the slide, there is a more elaborate proof, but I will walk you through it a bit more intuitively. And so we have our, basically, if you want to improve your classifier, you want to make it more fair, you can make predictions, and for the black people, you can start predicting for more of them to be at low risk by increasing the threshold. And only when I'm 60% certain that they will recommit a crime, I will predict them to be high risk, only 70%, and for white people, I will do it more quickly, or the other way around. There is also a website where you can do this. I hope it's in the slides, and otherwise I will make sure that it gets posted to you, where you can really play around and do this dynamically. But of course, in our validation set, we cannot make a black person white or a white person black. And so if we're shifting statistics, if we're changing our models, the only thing that will happen is that some of the minuses or pluses will go from right to left or from left to right, but never from top to bottom, right? And so our validation set has a fixed number of black people, a fixed number of white people, a fixed number of people with the true positive label, a fixed number of people with the true negative label. We cannot change that either. We can only change our predictions. So basically, it means that there are only 2 variables that we can play with. We can shift things from the top right to the top left, and from the bottom right to the bottom left, and the other way around. And so we can move pluses or we can move minuses. So there are 4 things we can move from the left to the right, and so there are 4 variables that we can instantiate. The percentage of pluses for black people that we put in the high-risk group, the percentage of minuses of the black people that we put in the high-risk group, and then the percentage of the ones that remain in the low risk is fixed, and the same for at the bottom. So 4 variables, and this is already a stretch, because this means that we could freely move, that we could change our model such that we could change exactly 1 plus to the right, and by playing around with thresholds there, usually you have this precision recall trade-off, and you can make more correct predictions of recidivists, but then you will probably also get a lower precision, and you will also be predicting the positive label for people that are not recidivists. But let's assume that we're in this situation, and we do not assume anything about how good we can make the model, so we can shift whatever we want around. So there are basically 4 parameters, and then there are also 4 equations, because here we want the percentage at the top to be the same as the percentage at the bottom for the low risk, the number of pluses that is there, and for the high risk there is a constraint. Let's just put it 4 constraints, because they're not necessarily linear. And then there are here also 2 constraints, namely we want to have that the errors, the probability of being high risk given that your plus at the top needs to be the same as at the bottom. With this 4/5 that was not equal to the a half was a problem. So we have 4 constraints, we have 4 variables that we can play with, and in the end it will turn out that there is only exactly 1 solution possible, and the only solution that is possible will be, and that's explained here, they can only be realized under very exceptional conditions. There are actually 2 conditions, sorry. The first one is perfect predictability or equal base rates. What does it mean, perfect predictability? That I can perfectly predict for everyone whether they will recommit a crime or not. In that case, I satisfy calibration, right? If I tell you you're high risk, 100% certainty that you will commit a crime. If you tell low risk, 0%. It doesn't matter whether you're black or white, my model is just perfect. Also, the errors that I'm making are also balanced, because I'm not making any errors. There are 100% true positives, 100% true negative rate. So perfect predictability is one, this situation where I can reach this mathematically. The other situation that I can reach this is equal base rates. And equal base rates means that when I start here, that the probability of being positive is the same for both communities. And that is not the case here, because we have 5 out of 9 in the black case and 4 out of 9 in the white case. And so we do not have equal base rates. If we have equal base rates, then it's also logical that we can satisfy it. Because then if there is no difference between the 2 communities, well, then the errors will be the same in expectation, the calibration will be the same, and the probabilities will be the same if they both follow exactly the same distribution and we do exactly the same things with them. Of course, this second case, that depends on your data. Sometimes it's true, sometimes it's not true. We can hope that it is true. We can hope that the same number of people are teachers, and male and female. We can hope that the same number of people are criminal, black and white in our data set, but that's not necessarily always the case, so that's just a reality that we need to deal with. And perfect predictability, and that's of course not realistic. I put there a picture, I don't know if you recognize it. It's from the movie, I forgot it. Anyway, the clue in the movie was that that they could perfectly predict who was going to commit a crime in future, and based on that, they would already lock up people before they committed a crime. So that would be possible if we would have that kind of models. probably not very desirable or ethical, but anyway, it's just not realistic. Typically, the COMPASS model was around 60% correct, so very far from being 100% correct, and that company really tried their best to make these predictions accurately as possible, and still they were very far away from perfect predictability. So in a realistic world, it's not possible to combine the two measures. Again, negative news. Later on, I will come back a little bit to, okay, so then what does this mean? What can we do if all this situation seems to be extremely hopeless? Another point, and there was a question yesterday, don't know where the person is, and that was about fairness and accuracy, and that was about, okay, so if we have our set of all the feasible models, all models that we can make on this data set with the attributes that we have and the learning procedures, if we then say, okay, we're not interested in all the models, but only in those models that satisfy some fairness constraint. For instance, they satisfy statistical parity or the errors are the same for both communities. Then if we look at the most accurate model that exists and we restrict ourselves, the most accurate fair model, then it's logical that we will have to sacrifice some accuracy for fairness. That's logical. If we pick the maximal element of a set or the maximal element of a subset, and the maximum will not increase, it will most likely decrease. So this is what is called the accuracy fairness trade-off, and it's a common assumption that the most accurate fair model is less accurate than the most accurate model. However, and this is an important realization, and it was only relatively recently that people really started looking at it in a mathematical way. Of course, if you assume that your training data contains errors and then you're measuring against the data that you use to train your fairness, you may get a fairness measure which is off, or you may get an accuracy measure which is off. In the case of our label bias, we had our black and white patients, and for the black patients, it was more likely that it was predicted a negative label while they should have gotten the positive label. If that data is used in order to evaluate our model, it could seem that our model is underperforming because it's making the correct predictions. It is correctly assessing whether someone is more ill than someone else, but we do not see it. We see a lower accuracy numbers because we are using the cost of healthcare instead. And so what the people from the paper here did, Wick and others, is they made some simulations and they could verify this. So what we see here are two graphs where we have on the horizontal axis every time the fairness, where the fairness measure is such that 1 is completely fair and 0 is completely unfair. And so they look at the probability of getting the positive label if you're in one group and divided by the probability of getting the positive label if you're in the other group. And so the probability that you will be assigned the teacher job if you're male divided by the probability of being assigned the teacher job if you're female. If it is 1, it means that these two proportions are equal. If it's more towards 0, it means that the males have a much lower probability of getting the positive label. On the left-hand side, you see the results on the data that is given to us, for which we assume that there might be some bias, and that's why we are using methods that learn fair models. And usually they have some kind of slider that we can say make it fair, more fair, extremely fair. And you see that it goes, the models, there is an evolution from left to right if we move our slider on our algorithm, so it becomes more and more fair. If we measure it on the data that has been given to us, and then the accuracy is going down. That's this graph that I'm talking about. But now, because it was generated by a simulation, they also had the underlying true data, and there you see that for the same models on the underlying true data, actually it could be the case that it became more accurate. The vertical axis is accuracy. I don't think I told you that. It's the F1 measure that is used to quantify the accuracy of the model. And so this means that it is not necessarily true that we have this trade-off between accuracy and fairness, because basically we're doing something similar like in, I don't know, in transfer learning, like we assume that we know something about the underlying distribution, which is not necessarily reflected in our training data, and we can have more accurate models by taking that into account. We know that our labels are wrong. If we take that into account, of course, with respect to our given data, we will score less accurate, but with respect to the true underlying distribution, we may actually score better. This was a simulation, and that's because it's very hard. It's almost impossible to find data sets that have both like some kind of fair and unfair labels. So in order to remedy that, we did some experiment where we gathered some data. So I agree with the previous speaker that it's sometimes very interesting to gather real data, to do surveys and get massive amounts of real data. What we did here is we started from a data set that is available in Kaggle, and that data contains results of students. I think it's Portuguese students, and they also have a lot of characteristics, like, for instance, do they like to go out very often? Do they drink a lot? And these are self-reported numbers. How often do they study? How many hours per week? Are they often absent in the lecture? Do they have a lot of hobbies? Are they in a relationship? This type of data is there. If you then look at the grades of the students are given, and we can then see if they passed or did not pass. It's the average of their first year, the first bachelor, I think, that was in the data set. And there we see that it's 50-50. People have a similar probability of passing. Boys and girls have the same probability of passing. So there is actually no real bias in the data set. And these are our ground truth labels. So we will assume that this is the thing that we would normally not observe. And instead what we did is we used a lot of volunteers and we presented these profiles to them, and they needed to make some prediction, will this student pass or fail? One thing we saw, and we were really hoping for it, and we were also nudging people a little bit into that direction by giving them some incentives. You can check the paper if you're interested in the details, like we were showing them some statistics on average of performance, academic performance of boys and girls, where girls were usually performing better than boys in general, but not in this data set, but in general. And then students had to make the prediction. They didn't see the true labels. They also needed to make a ranking of these 10 profiles, who is most likely to pass the course and who is less likely. And one thing we saw, and that if people were ranking them, that this was introducing a bias against the boys. And so the performance of the boys was systematically underestimated by the volunteers. So what do you see, for instance, in the first graph, one here? And so blue and red are boys and girls. And so the red are the girls and the blue are the boys. And this is the histogram of the predicted grades. If you would plot the histogram of the true grades, then you would see that the two histograms are completely overlapping. Here you see that the effect is not dramatic, but there is a shift. The red bars are larger on the right end of our histogram, which has the higher grades, and lower than the blue bars on the left side. And so girls are more likely to be predicted to have or assessed to be more likely to have a high grade than boys. Then the prediction rank versus the true rank. That was the experiment where we offered 10 profiles, now rank them. And so we have the true results of the students, and we have the predicted rank of the students. So we can rank the students according to the true results, and we can rank them, or we take the ranking produced by our volunteers. And there you see that for females and males, there is a different distribution again. It's again a histogram where the girls have a higher probability of getting rank 1, 2, 3, 4 than the boys, and the lower ranks are reserved for the boys by our volunteers. And then the last one is the difference between the predicted and the actual grade. So that was a third experiment where they did not need to predict whether they passed or failed, but what would be the grade. And then we compare the differences, and again, the same results is observed. So this was a very useful data set, and it's also freely available. It's, you can download it from Kaggle. If you want to test your algorithms, where they have a data set that has both the ground truth labels, so what grade did they really obtain, and the predicted labels that contain some bias, predicted or some labels that were given by volunteers. So if we would now learn a model on these labels given by the volunteers, and then we could compare them to the ground truth labels. So we can basically repeat this experiment that was here. This question.
Can you think about generating synthetic data sets? But in this case, you would kind of guide the generation by putting on the technical aspect that you need to maintain the fairness of the generated data.
Okay, so the question is, so if you can think about a way to generate synthetic data where you start from a ground truth which is fair.
Since you have data, fair, you assess that the data that you have already with the ground truth is fair, but it's not enough to build more. So you would like to generate synthetic data, but we need to keep an eye that even the synthetic data should be fair in order to have this fair model that you are looking at.
Okay, so you have real data which is fair, and then you generate synthetic data which is also fair and which has a similar. Okay, and which should also be fair, which is then probably a case for data privacy, maybe that you can share the synthetic data and then learn the models on that one. Yeah, that's definitely something interesting that people are also looking at, like how to generate synthetic data that follows a similar distribution as real data. But
paying attention to what we call the data drift. Mm-hmm. The synthetic data should not be very far from the original one. But now we are putting on a very interesting feature. Should be very close to the original one, but also as fair as the original one. So I think that's very nice topic that we also can work on it together.
Yeah, okay, definitely. But maybe let's take this at the end or offline, because I think it's slightly distracting from what we were trying to do here. No, apologies needed. Because what we're trying to do here is to mimic a situation where labels have some bias, and now we want basically to test this, but not on synthetic data, but on real data. And will it happen in reality? Why is that? Because generating this type of synthetic data, it's not easy. Like if you look in the paper where the authors did this, it's actually relatively simple. It's hard to generate data that looks like real data. And what is the reason why there is bias? So we do not necessarily know. Like here in this case, why do they believe boys or girls are underperforming? It's like direct discrimination, because you look at the characteristics and then you say, okay, this looks like a good student. Oh, it's a boy, so let's give a slightly lower grade. Or it's a girl, let's give a slightly higher grade. Or maybe boys are more likely to have a high alcohol consumption, and all the influence of the alcohol consumption is overestimated, and because of that, the boys get the lower grades assigned by the volunteers. We do not really know this, and we want to mimic such a situation where we don't really know it, but it's really messy, and there are all kinds of dependencies between the variables, so it's also not very easy to clean the data. And making long story short, on this data set we observe very similar behavior. where again on the horizontal axis you have the score for the discrimination by the algorithm or the bias of the algorithm on the vertical axis. The accuracy, it's a rather difficult task, and so you see that the accuracy goes up to 75% and not too much higher. If we look at the labels that are given by our volunteers, then you see if you increase the fairness of our model, then the accuracy for predicting the labels given by our volunteers goes down. The one on the right-hand side is we learn our model using the fairness measure. During the learning, we do not use the true underlying labels, but only the tainted labels and our additional information, our assumption that boys have been discriminated by our volunteers. And then you see exploiting that information can actually lead to a situation where we do not have a trade-off on the true underlying distribution. We actually score a higher accuracy if our model becomes more fair.
How big is the data set?
So the question is, how big is the data set? It's, if I'm not mistaken, it was like 2,000 instances. It's not extremely large. So it's definitely some future work, maybe not for us, maybe for someone else, to also extend this. Yeah. All right. Voila. So we had our group fairness measures, some trade-offs and impossibility results. And let's now also look at individual fairness measures. So with the group fairness measures, what we try to do there is we try to look at a classifier in its entirety, a model in its entirety. Does it discriminate against the whole community? What we want to do with individual fairness, then we want to see not individual cases. Can we identify people in our data set and that have been discriminated against, which is also kind of interesting. Of course, you can turn every individual fairness measure into a group fairness measure, whereby you can go over every individual, look at what is the probability that this individual was discriminated, and then aggregate it at a group level. But it's also interesting to look at the individual level. So for instance, someone comes to you and tells you, okay, I think I've been discriminated by the algorithm, then you can use such an individual fairness measure. And so first type is situation testing. And situation testing is something that comes from social sciences, where basically they see if a certain procedure is discriminating people. And for instance, they take CVs and they make a male and a female version of the CV. They send it to companies, and then they see which percentage of males are invited for a job, which percentage of females are invited for a job. I think in France at a certain point they did it with job applications where there were ethnic names on it, or local or just French names on the CV, and then they saw there was a big discrepancy in how many people were invited for a job interview between the two CVs. So this is a situation we like to mimic, this kind of situation testing. And so basically we can look at an instance in our data set for which we want to know whether it was discriminated or not. We look at instances which are in the neighborhood, the k nearest neighbors that are of the other gender, and then we can see, and then we can compare the probabilities. And so here, this is one specific approach. And in the paper, it's already an old approach. There have been lots of improvements, but this is the original idea. So we take an instance. In this case, 4 nearest neighbors is taken. So we take the 4 nearest males, the 4 nearest females, and so we learn a probability in the neighborhood of this instance. What is the probability that a male versus a female gets a positive label? Why do you take both the k nearest neighbors for the females and for the males? And that is because otherwise everyone who got a negative instance will be labeled as being discriminated against. And so if you're in a region where 10% of the people get a positive label, and 90% the negative label, and you got the negative label, and you look at the 4 nearest neighbors, then there will be 10% probability that they got the positive label, and you yourself, out of 1, there is 0 that got a positive label. And so you cannot really compare. You need to have sufficient statistics in the neighborhood. So this is one approach about individual fairness, which is quite popular. So likes need to be treated alike. But then again, this is basically moving the problem. When are 2 instances alike? Then the typical answer would be we only consider attributes that matter. So the education, let's say it's for a job, the grades that someone has, the experience that someone has. We do not look at the length of the person, the weight, maybe not the place of birth, not to take into account ethnicity proxies. And the languages that someone speaks, maybe we can take it into account for some jobs. Like if you're working as a secretary at the university, it's important that you can speak English, for instance, because of all the international guests. If you're at a reception in a hotel, you need to speak different languages, so it makes sense. But maybe not if you're in construction worker, then maybe this could be used as a proxy for ethnicity of a person. So it's very hard to consider the attributes, and then like when are 2 people close to each other? Like if you have an engineering degree in IT or an engineering degree in building, like how far are they apart? Like is it 1.5, and is it farther away than someone who has a degree in gender studies? Yeah, probably these 2 are closer, but it's very hard to assess. And basically we are moving our problem a little bit, and from defining what is fair to defining when 2 people are alike. We know that we think if 2 people are exactly the same, but the gender is different, then we want them to be treated alike. But if 2 people are exactly the same except for their diploma, then they should not be taken as being alike. So this is information that needs to be imputed in the system by someone externally. And like gender, not okay to measure the difference between people. Education, okay. Languages spoken, half okay. So that's, and basically the problem is moved to determining a good distance function. Some other approaches that nowadays are gaining a lot of interest are causal-based fairness measures. And basically the question is very similar as individual fairness. How would an individual have been treated if she belonged to the other group? In case of gender, if she had been a he, would this person have been hired? If the treatment would have been different, then there is unfairness. But this, in causal-based fairness measures, this is based on a causal model, and a causal model is a rich formalism to reason about how data is generated and which things depend on which, and which connections between variables are correlations and which ones are causal relationships. So for instance, and this is an example from a paper from Kussner and others from 2017, where they look at some characteristics that they have from people. And so the gray ones are the ones which are observed, and the open one, the knowledge, and that's one which is not observed. And basically, and that's what we're doing always. We want to assess how qualified someone is to be a student in our institute. So we want to assess what is the knowledge of this person or the intrinsic capacities of this person, and we can only observe this indirectly. Like you can do an IQ test, and then you can have a proxy for the true intelligence of a person. And here there are a number of characteristics that could be used. GPA, the grade point average, LSAT, another a test that students can take for entrance in universities, and some kind of uniform test. And then the FYI and the first year average. That's like probably our target variable. And we want to assess the first year average, which students are going to be successful based on their GPA and their LSAT scores. And they are all proxies of knowledge of a person. And then we also have the race and the sex of the person, let's say. And in this paper, they show that in some situations, there is actually a causal relationship from race to GPA, from race to LSAT, and from race to the first year average. Why is that? Because people with different ethnic backgrounds typically go to different schools, or like a large proportion of them goes to different schools. Some schools are better, some schools are worse, which affects their grade point average. Maybe some schools are easy giving higher grades than some other schools, so there might be a relationship there. Same for the gender of a person, and so there is some separation of boys' school, girls' schools, for instance. LSAT, there very often language plays a role. If you're a native English speaker, you will score better on a LSAT where the questions are in English than a non-native speaker. And then the first year average, and for the same reasons, may be affected. So this means that if we basically want to evaluate the knowledge of a person based on these 2 or 3 characteristics that we have, and GPA in the LSAT, or GPA, LSAT, and FYA, if we're recruiting students for a master program, and we assume that there are these kind of causal relationship. Based on that, they can you can assess the model, and you can make this kind of what-if analysis, and you can make these causal inferences. There's a whole theory behind it. Judea Pearl has a whole book on it. It's very interesting, I think, especially if you're also interested in this fairness topic. Basically what it allows to do is this kind of what-if analysis, where we look at what would have been the outcome given that a person has certain characteristics, and we take a certain intervention. We do T is equal to T. T stands for treatment. These causal models, they come from or have been used a lot in the medical domain. And there the treatment would be, we give medication A or medication B to a patient. And so what would be the outcome for a certain patient that has certain symptoms if we apply medication A, and what would have been the outcome if we would have applied medication B instead of medication A. It is well known in that domain that this is not equal to the conditional probability. We cannot just take all the patients with symptom X that got a certain treatment A and all patients that got a certain treatment B, because the treatment may depend on the characteristics of the patient. There might be a very expensive and rare type of medication, and a very common one, but known to be somewhat less effective. So the doctors only give the very expensive one to those patients who are already in a very severe condition. If you do that and then you measure the conditional probability, it will seem as if the cheap medication is much more effective. But that's because you're giving it to patients that are already in a better shape, and you only give the expensive medication to patients that are in a much worse shape. Other known examples of this effect is if you look at the success rate of operations in a university hospital or in a general hospital, and university hospitals will score worse because they take on the more difficult operations. And in some books on causality, another example they give, if you go to sleep with your shoes on or with your shoes off, and you look at the probability that you have a headache in the morning, if you went to sleep with your shoes on, then there is a much higher probability that you wake up with a headache. But that's probably because there is some confounder, and namely that you were drunk last night. But here, these techniques that have been developed there can also be used in this context, where basically we can do some kind of inferences. So we have a male that has taken the tests, and basically now we want to see what would the test results have been, or let's say someone who is a non-native English speaker, and you got some results there. what would have been the result of this person if he would have been a native speaker of English. So if we replace the race variable there, we replace it, and what would have been the outcome then. And in that way, they can make some derivations, and they can change the LSAT score of a candidate. If you change the LSAT score, that does not influence the first-year average, but changing the knowledge of a candidate will change the LSAT, GPA, and first-year average, but not the race or the sex. And that's basically what the causal diagrams are saying. This also helps us to make this kind of derivations when we were looking at this conditional statistical parity, where we were saying, okay, we have the gender of a person that affects whether we are hiring him or her as a professor, but then we also need to take into account which diploma that they're having. We're hiring someone in the IT department, there are more male candidates with an IT diploma, and it's not uncommon that it's more higher probability that a male will be hired. For social sciences, it might be the other way around. Then it's logical. So that will be reflected in this type of diagrams, where then there will be the knowledge of a person, the capacities of a person, the gender of a person, and then study will depend on gender. There will be a relation, an arrow going from gender to the type of study. And when we make this type of analysis and the type of study, whether someone is suitable for a job, there will be an arrow there, and then it will automatically be taken into account. Here is something that we could use, for instance, in the case of recidivism, in the COMPASS case, if we want to analyze it, or that has been used in those papers to analyze it. The age of someone may affect how aggressive he or she is because of hormones, the gender, for instance. If someone is more aggressive, it's more likely that he or she is a recidivist. It's more likely that there is a prior conviction. And then there might also be a direct connection from race to prior conviction, from race to recidivism, the recidivism labels in our data set, because maybe there is over-policing of a certain ethnicity. And so this type of models allows us to take all this fine-grained information into account and to basically the paths that go from age to aggression to recidivism. These are paths that we want to take into account, but the direct path from race to recidivism is something we do not want to take into account because we're assuming that this is a bias that has been introduced in our data set because of over-policing, for instance. Voila. So these are called path-specific effects, and that we want to measure. And then identifiability means it refers to conditions under which this kind of path-specific effects can be measured, which is not always the case. And depending on the situation, you cannot always measure these path-specific effects. And for instance, here it could be that we are allowing a correlation with race and age, and we are allowing that there is a correlation in our results between race and our prediction of recidivism, but only insofar that it can be explained by prior conviction. So this is this conditional statistical parity type of principle. And because the direct arrow from race to recidivism made it red, that's a path-specific effect that I want to filter out. But the path that goes from race through prior conviction to recidivism, that's one that can be taken into account. Voila. And so we have this whole bunch of fairness measures and group fairness measures and individual fairness measures that we can use. Like an intermediate summary, many competing definitions. So how can we define when a decision is fair? Conclusion, there is no universal definition of fairness. So maybe it's situation dependent. And how can we select then the best measure? There have been a couple of papers. I think the most concrete one is the Fairness Compass, which is made by some people that I know that are researchers at AXA, the insurance company. And they're, of course, very interested. They see this AI Act coming their way. They need to measure when their models are fair or not fair, but then how can they do it? They made some kind of big taxonomy looking at, and of course, we can do some things there. Like if you look at statistical parity, where we say with the example, the healthcare example, we assume that our labels are wrong. We assume that there is no difference between health situation of white and black people, but our labels are pointing in a direction that there is a difference because we use this health cost, and we'll not reiterate the complete example. If that is the case, then it makes sense to use or to measure our fairness using statistical parity. If, however, we assume that there is a difference between males and female candidates because of their diploma, then maybe it's conditional statistical parity. And this kind of diagram helps you a little bit to navigate through it. So that could be one help, and in the end, it ends up with which measure that you should take. Then there are also some theoretical works. In the interest of time, I will not go too deeply into that because there are other topics that I think are more interesting. But if you're interested in that, then the paper of Friedler and others is definitely an interesting one. They consider 3 spaces and correspondences between the spaces, and the spaces they consider is what is the true underlying world, then what we observe, and then what we predict. And so what we observe may not be exactly the same as what is the true underlying world. And so we may observe, there might be sample bias. Not for everyone we are observing a label, or there might be a label bias, and so the labels that we observe are not exactly the labels that we want to predict, and then the connections between these 3 worlds. But anyway, my takeaway on measuring bias in data, I'm conflicted myself internally a little bit, and like, okay, does it actually make sense to look at fairness because they're always interacting? For me, I see them actually as red flags. So you can use a fairness measure if the fairness measure is off, and then it's like a red flag that is raised and you need to find an explanation. More males and females are being hired in my company by our automated decision procedure, or being suggested to be hired. Okay, is there an explanation? Maybe I can go look and find, okay, there is diploma. If I condition on diploma, it goes away, then check, it's fine. If I cannot find the reason, then maybe there might be a bias and I need to look a little bit deeper into that. So that's basically what I say about justifying discrepancies. If you want to read a more social science perspective from that, then there is the paper of Sandra Wachter and others, which is quite interesting to look at it, where they explain about why they think fairness cannot be automated. There cannot be one single measure that you can pick, put in the law, and if the models satisfy that measure, automatically it will be fine. And basically they contemplate also on some examples there. Voilà. So after a lot of the negative results, let's now look at a case of a fairness audit. And so where a model is being used, researchers have been looking into the model and wanted to assess whether the model is fair or not. And the case that I think was rather well executed. It's the Internal Revenue Services in the United States that was researched. And so they basically do the tax audits. And in this case, they wanted to study the differences in tax audit rates between black and white taxpayers. In the United States, again, very polarized with respect to racial issues. And so they wanted to study, are black people being over-audited by the IRS in comparison to white people? And if so, what is the reason? There were some issues in this study. Incomplete data, and incomplete, very common in this type of fraud detection cases, because you cannot check everyone. So you need only, so you pick out 10% of the cases, for instance, and you go and check those 10%, so you get the sample bias, definitely. And also no information on ethnicity was stored in the data. So this is also an indication that if there is a discrepancy between how white and black taxpayers are being treated, then it must be some kind of indirect discrimination because you cannot directly infer the ethnicity from the data. It's not stored there. So they have 148 million tax returns there. There you already see out of this 148 million, only 780,000 have been audited. And so for those, they know if there was fraud or not, or at least fraud detected or not. And they also have, and that's also quite interesting, 72,000 audits of random samples from the National Research Program. So that's a separate program that exists next to the IRS, and they're independent, but they just randomly select samples, so tax applications, tax returns, and they check whether there is fraud in it or not, while the 780,000 selected by the IRS, and those to a large degree have been selected based on some suspicions that they have. Maybe they have been selected by that these are about large amounts, or there are some discrepancies between income and outcome, or the percentage of tax that someone needs to pay in the end is very low. Anyway, there are some clues there, and for which they have been selected. The 72,000 have been selected completely randomly. So the first issue, because we want to look at the differences between the two communities, is that ethnicity is not there. So what they did is predict ethnicity based on name and postal code. And this is why what they use is an extremely simple system, which has a rather complicated name. It looks like it's quite something, a Bayesian improved first name and surname geocoding. Basically what they do is a little bit like if a naive Bayes classifier, they make this assumption that the probability of observing a first name, a second name, and a geocode is like a postal code, given the ethnicity of the person, and that these three characteristics, first name, second name, and geocode, that they are independent given the ethnicity of a person. And just like a naive Bayes assumption, if you do that, then you can, just like in naive Bayes, turn it around and make a prediction of the ethnicity of a person based on these three characteristics. The formula is down there, but that is like high school mathematics. They can show, they showed in the paper that this is relatively accurate to predict the ethnicity of the person. How did they show this? And they used publicly available voter registration records from North Carolina, and those voting records, they have nothing to do with taxes. It just contains first name, second name, and geocode of the people, but the people can also self-report their ethnicity. It's self-reported, so there might be some errors there, but it's actually a relatively good clue, and they show that their prediction is quite accurate there based on this data. And in this way they can add, because it's not perfect, they basically show two techniques to then compute their statistics based on this gender that has been, based on this ethnicity that has been added to the data set. Because of that, we always have lower and upper bounds on all statistics that we show. And they show that with a very high probability it's between these two bounds. And they show in the data that the black community is audited at a much higher rate than the general population. So the audit rates for blacks is between 0.84 and 1.34 percentage points higher than for non-blacks. That may seem very low. And so if you look at the percentage of blacks being audited, it's the percentage of whites being audited plus 0.84, but the base audit rate is only 0.54%. So this is, if you're a tax evader in the United States, this is good news. There's a very low probability that you will be audited, actually. So blacks in our data set are 2.9 to 4.7 times more likely to be audited, depending on how well you trust your estimation of the ethnicity. So this is basically statistical parity that they're measuring. And so this is what I'm saying. This is like a red flag that is being raised. There is a big difference, so we need to investigate further. And we can then go to conditional statistical parity. Maybe it depends on the type of fraud that is being committed. And there is this system of earned income tax credit, which is a specific type of tax refund, which is a little bit like benefit payments, depending on your income and family situation and so on. And you may deduct something from the tax. A relatively recent principle, if I understood properly. And so when auditing, it could be that they were specifically targeting people that were applying for this EITC. But it turns out that this is not the case. So what they do is they do this conditional statistical parity. So we split up in those people applying for the EITC, people not applying for that, and then we see that black taxpayers claiming the EITC are again between 3.9 and 4.4 times more likely to be audited than non-black taxpayers. Other reasons, maybe it can be explained by differences in income, family size, household structure. Again, it turns out not to be the case. The differences remain. I refer to the paper if you're interested in the exact statistics. Or maybe blacks are more likely to underreport, but again, this cannot be fully explained by the difference. And so what we see here is something that is very much alike the equal opportunity. So now we're going to look at those people and their real labels, and depending on their real label, how likely is it that they will be audited or not audited? Here in this case, the real label, this you see on the horizontal axis. This is the amount of underreporting. And so you're reporting income and you're underreporting, and it can be more severe or less severe. The histogram you see is for black and white. And you see that the blacks are not dramatically, but like slightly overrepresented when the underreporting is higher, and there the whites are overrepresented when it is lower, and so the whites are less likely to commit this specific type of fraud. But then for each of the buckets, so they condition on the label, on the true label, and the true fraud that is being committed. And then you see these two lines there, and one at the top and one lower. This is the rate for each of the buckets at which the black population is audited. That falls into the black into that bucket, and then the lower line for the whites. So even if we look at the true amount of fraud that is being committed, we would expect to see the same audit rates if equal opportunity was satisfied. And so again, somewhat problematic here. Again, a red flag. Now, in order to generate this graph, it was important that we had these random samples, because basically what we want to have is a probability of an audit given the ethnicity of a person and the amount of fraud that was committed. This is a statistic that you cannot compute on the data of the IRS, because the data of the IRS has this sampling bias, and people are being audited. Well, there are differences in probability of getting audited, so you cannot compute this probability. However, you can use, again, combination, like Bayes' rule, and you can split it up, and then have the probability that you have a certain amount of fraud, given that you're audited, and your ethnicity. That you can get from the IRS data. You just look at all the people that are being audited, you split them up in black and white. You look at the amount that the audit of underreporting that was there. You can look at the probability that you're audited given your ethnicity, because, okay, we have these 147 million tax applications or tax returns for which we have the ethnicity. We know who of those were being audited, but we do not know the probability of a certain amount of tax fraud given the ethnicity of a person. and that you need in this formula, and that we can get from this independent data from this random sample. Because in this random sample, and there we can again apply, impute the ethnicity of a person, and we can assess. And now they are randomly sampled from the whole population. Voilà. Yes, a question.
There are too many information to digest, but so the gist of this plot is that the two curves related to the audit rate ideally should be as close as possible to each other, but also maybe proportional to the amount of differences that we have in each beat. Is that one of the takeaways? Or?
I completely agree with the first. So let me repeat. And so and there's a lot of information in the graphs, but the gist of it, okay, what would be good is if these two curves would have been the same, definitely. And then there is also the question, shouldn't you expect the curve to be going up? Because the more to the right you go, the higher the amount of underreporting is. And so the more severe the fraud is that has been committed. And so you would expect that the probability of auditing goes up as the amount goes up. Yes. And so the first one, I completely agree. The two graphs should actually be collapsed. That's the same like in the compass case. If you deserve to be in prison, it shouldn't matter whether you're black or white for our model to predict whether you should be in prison. Here it is, if your amount of underreporting is, let's say, $3,000, it shouldn't matter whether you're black or white. It should be the same probability that you're audited. And that's why the two curves should be the same. Here, indeed, more to the right means more severe fraud. So you would expect it to go up. Now, in reality, there are some additional constraints that's also described in the paper. Things that are more to the right are usually more complex types of fraud, requiring more specialized personnel, and they might be understaffed. And because of that, the more severe cases or the more complex cases are audited at a lower rate than the easier cases, let's say.
I would like to suggest like a hypothetical situation. So let's say that the resources of the tax system is limited, and obviously, like let's say we have another level of analysis. So thinking about like how much of resources the tax system has, and potentially would like to be able to tax as much as you can and like avoid fraud and basically tax avoidance. And now the question becomes like, if you know that, for example, one group has proportionally more chance of avoiding tax, wouldn't you invest more resources into basically auditing that group more than the other? And so then question becomes that given this extra level of analysis, then coming back to the question of fairness, like, okay, what would be the fairness in this case? Because, I mean, there is a grander scale of things and more like aspects to take into account. Mm-hmm. So what can we say about fairness?
Yeah, so yeah, it's becoming too much to remember everything and to react. But if I understand correctly, it's like, okay, isn't this pointing that maybe resources are being allocated not in the best possible way? And because there was this argument, okay, we should try to get as much fraud, the largest amount recovered. And then looking at the curves that are sloping off, again, that's indicating that we are not allocating the resources in the right way. We should be more allocating in the more complex cases. It's partially a political decision. It's not only about recovering as much money as possible. It's usually, if you talk to people in tax administration, they don't look at it as like a business model. It's not like we're trying to make as much money as possible. It's more like to increase adherence to the tax legislation. And then it could be worthwhile to catch maybe more people, to spend resources in order to have more cases uncovered, rather than going for the largest amount of money, or maybe to target specific types of fraud that you consider as more unethical than other types of fraud. So that could also be the case, but definitely that's a very good remark, but that's also largely political, and we'll also see in a couple of minutes there. But the thing that is really not okay is this difference in the two curves, because that means that two people that are in the same situation, behaving the same way, that there are then differences between how the rate at which they are being audited. So then the researchers also did, and so they made some, thought up some reasons why. Maybe it has to do with what we're optimizing, the object that we are optimizing. And this again is for me an illustration like how complex the situation around fairness is, and how it can happen without you having the purpose of discriminating. So what they studied is, okay, so they don't know the models that the IRS is using. They don't know which objectives they are optimizing, and they only had the outcome, who is audited, who is not, and now let's do statistical analysis. They find out these differences, and now they want to find the reason why are there these differences there. And so they built their own models and then evaluated their own models and how much fair or unfair are these models. So one objective that they looked at is maximize the number of fraud cases detected. The other one is the maximal, to maximize dollars retrieved. So for the second one, you will learn a regression model and then rank the cases according to the predicted amount of fraud, and then start checking from the highest amount to the lowest amount. The first one, you will learn a classifier that predicts a positive or negative fraud or non-fraud, and you're trying to optimize the number of the recall. You can focus on specific types of fraud. You can focus on under-reported income. So I earn 1,000 euros, but I'm saying in my tax application that I only make 500 euros, that's underreporting. Or I can focus on unjustified refunds. Let's say a company during COVID times, and I'm claiming that my shop had to be closed during COVID, but it is not true, because if I claim that it was closed, I get a tax benefit of 1,000 euros. So that is an unjustified tax refund. Then two different types of fraud, and depending on which you concentrate, it will be different. And then they could make this type of graph here. And what you see on this type of graph, let's first look at the two red lines and the point that is called status quo. So on the vertical axis, you see the disparity. And so this is how much unfair the model is. So if it is 2, it means that 2 percentage points, that the probability of being audited for blacks is 2 percentage points higher than for whites. And that is the current situation. So now we can learn a model on our data. We can apply our models. And then we can start checking 1% of the people, 2% of the people, 3% of the people, until, and here they went until the 3%. So my classifier predicts this person has 98% probability of fraud, this 96, this 97. We will rank everyone. We start with the highest probability, and we do the top 1% or the top 2% or the top 3%. The more we do, the more dollars we will retrieve. And that is what is on the horizontal axis. That's in millions. And so in the current situation, the red point, the red vertical line from the status quo, so currently they are retrieving $2 billion in fraud. And if depending on which model they choose, it will be more or less. The oracle, so that is, I cannot point very fine, but the one that extends to the right, this is if we would have perfect information. So for every person that files taxes, we know perfectly the amount of fraud, and then we just we start with the person with the highest amount of fraud, lower, 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 if you would use that as a model, then actually the audit rate for whites would be higher than for blacks. Maybe not unlogical, and looking at the social situation in the United States where the black population is poorer, so the highest amounts of fraud will probably be with the white population, so that's the oracle one. If you use a regressor, so we are explicitly targeting, we want to have as much dollars retrieved, then there is the thing at the bottom. Of course, if we check 3% of the people, we will retrieve less dollars. We only go halfway and not to the full extent of our oracle because our model is imperfect. So we will not retrieve all the dollars, but only like half of it if we use that one. If we use a classifier, so we want to optimize the amount of the number of people that committed fraud, and then you have the second one. And so I go from the top. The second one is a classifier, so we want to increase the number, and then the top one, that is if we concentrate mainly on one type of fraud. So we mainly concentrate on refunds. So people that are claiming refunds that they are not eligible to, and that one almost intersects with the status quo point. So most likely the explanation for the discrimination here in this case, or the different audit rates, the bias, let's say, and let's leave it to the legal people and the politicians to call it discrimination or not. And it's probably because they're concentrating on the one hand on optimizing the number of people that are caught, and secondly, they're optimizing a specific type of tax fraud, and namely the refundable tax fraud. Voila. Yeah, there is some more explanation in the slides. Voila. So main takeaways from this case. How to circumvent a missing sensitive attribute. I think this is like really important to also illustrate that, because this is a critique that is heard very, very often. Also, with respect to the European AI Act, companies are complaining, or we need our models to be fair, but all these fairness measures assume that we have our sensitive attribute available. But then there is also data privacy, and if we collect ethnicity of people, then we need to really be aware, and that this is not always possible in every situation, not always allowed. And then we really need to protect our data. Here is an interesting case where it is shown how in a real case you can circumvent this missing sensitive attribute. The measures are used as red flags, which I think is very good. You have on the one hand the ProPublica, who for the Compass case, predicting recidivism, is yelling like, oh, this is discrimination based on one measure, but then does not investigate why it is the case. On the other hand, you have the company that on the basis of one measure is saying, no, it's calibrated, so it's not discrimination. I don't think that's a good way. You cannot certify fairness of a model by just looking at one measure, but you can show that there is a whole procedure in place in your company where you look at the red flags, look at these different measures, and if a red flag is raised, and then basically you're investigating it more. And also has seemingly neutral political choices. We go for specific types of fraud. We go for catching more people rather than going for higher amounts. Can have far-reaching impacts. So the types of fraud to tackle, the objective and the target. And I think the paper is an interesting blueprint on how to audit, because now the politicians have a much better insight in what were the potential problems there, and can make decisions, can say, okay, given this information, we think it's fine. We can keep it as it is, or maybe we should target different types of fraud, or maybe we should target more the amount of fraud. As time is running out, I will just 1 minute very quickly tell you about what you can find in the slides on the other topics. And so the fairness interventions This is techniques that if you say, okay, I want to target a specific fairness measure, that automatically learn models that are fair by design, that satisfy this specific measure. They work pretty well, and they look at this accuracy-fairness trade-off in most of the cases. They try to satisfy a fairness constraint and then have under this constraint as high accuracy as possible. And they can do this by different, intervening in different places. The input data, if we assume that we have a label bias, we can try to correct the labels, for instance. If we assume that there is a sampling bias, we can resample our data set. Or we can have a penalty. We have an optimization procedure where we introduce the fairness measure as a penalty if you're unfair. And you're not only interested in having the highest accuracy, but also relatively fair. Or we can learn a model and then in the end, tinker a little bit with the model and change the model itself. However, and this is the last main conclusion, so these are adversarial approaches. And however, what is very often happening in these cases is that if we make a classifier that is optimal, so I have a classifier which is very accurate, but it's not fair. So we want to make it fair, so we need to make it different. Some of the predictions need to change. For instance, we are predicting for 20% of the females that they should be recommended a teacher job, for 10% of the males that they should be recommended a teacher job. Now we want to make the model fair. Well, these provably optimal classifiers can be shown to make mistakes on purpose. It's like we perceive it as a trade-off, like, okay, we will make the situation better for the blacks, and we can do this by making it a little bit worse for the whites, and in this way we will balance it a little bit better. And so the situation for the whites, for the blacks, receiving a loan, let's say, and so we will do it like this. But that's not the reality. And the reality is we can, this is already the best possible model that we have for the blacks. There's just a lot of uncertainty here. This is the best possible model for the whites. This cannot be made better. And if we make this worse, this one will not become better. This will become worse. So we'll just randomly be picking, and this is what some of the algorithms really do. We just randomly pick a white person and we give them a negative label. Just not out of spite, but because we want to meet this constraint, and that's just the only way. We're convinced that this person deserves a positive label, but we give it a negative label. And so that's why I often compare it to this dilemma. What shall we do? More accurate, more fair? So that we just run over the people and then just shoot someone from the other community as well. And so and basically let me stop at this point with my conclusion slides. Voila. That unfairness is a real problem. It cannot be solved by automatically applying the right tool, but I hope I've convinced you to, if you apply models in the real world, and to look at some of the fairness measures, use them as red flags, and then maybe inspect the situation a little bit better. Thank you.
Thanks very much for the great talks. What you've clearly shown that fairness is a lot about political decision making eventually, and there is probably a lot to do for philosophers and others about that as well. But I'm wondering, what are the open questions kind of from the computer science side at the moment?
So, I think a big open area is. And I'll just pick a slide for that. It's like in which situation what fairness intervention should be taken. So what is depicted here is we have a real world where we assume that the fairness criterion holds. We assume that males and females are equally capable of being professors. So because of that, we think they should be hired at an equal rate. Then we have what we observe, and what you observe is not that this is the case. More males are professors than females in computer science, for instance. So there is some process that took place in here where the bias was introduced. Label bias, selection bias, a combination of those, maybe an unknown type of bias until now. And what's happening now is that this part is completely ignored. And basically many people have been making algorithms that try to learn our models on our observed data, satisfying some fairness constraint. And then there are some ad hoc rules that people can use in order to select, okay, maybe in this case it should be statistical parity or conditional statistical parity or equal odds, or maybe something else, or maybe a combination. But there is very little research about how these two are need to be combined. And because in our opinion, and this is Marco is a student of mine with whom I'm doing this research, and basically we're saying, okay, the fairest situation, actually you should evaluate fairness by looking at which model would be the most accurate in your original unbiased world. And there we show that a lot of those combinations of algorithms that is used in specific situations actually makes it worse, and in other situations it works. But I think that is really an important thing. Also to give advice to companies, because now it's like there is legislation coming their way. Your models need to be fair. You can measure it in this way, that way, or that way, or that way, or you can invent your own way, and then well, you can make it fair in this way, and then someone will claim it's unfair in that way. Like what will keep up in a law case, and there we need more to close this loop.
And this is doable?
Yeah, to some extent, I believe I'm a believer in having this system of audits and certification, rather than having a simple measure or applying this algorithm or that algorithm, and then it will automatically be fair. I think there needs to be some awareness growing of these issues, certain procedures that can be followed by companies. Yeah. But it's a little bit like with privacy, and there as well, you need to protect the data of your customers. And in order to do that, you cannot write in a law, you need to have this type of privacy, or you can take that measure or that measure. You also, as a company, you need to follow up what is common techniques to do that, or what are the current techniques to do that. You need to patch your software. It will never be perfect, but there are different steps or procedures that you can follow.
Would it be fair?
Yeah, just go ahead. I will repeat it if it's not recorded.
Would it be fair to say that the issue of fairness is fundamentally related to the sample size and the number of features? Because most of the problems that we are dealing with are like multivariate problems. It's not only about like one variable or the other, but because we don't have enough data, we don't have enough observation of the attributes of a problem, then we inevitably focus on one or few variables that we think are important to fairness. And so, like, this is kind of first question, but then what are the implications in this age of large models? And now we're seeing there are more emerging models, emerging, that they incorporate large amount of data. Would that be a better direction to go, or like would that change the notion of fairness? When we have large models that can incorporate lots of data, would that lead to more fairness, better fairness?
Mm-hmm. I think in general, better models will usually be also more fair models. But it's not only a data problem. And what I think is also an important aspect is that we should disentangle the things that are like data science, computer science related, and things that are policy. let me illustrate that point. Suppose insurance, and you only know, the only information you have is about the gender of a person, and males make 60% accidents, females 40% accidents. So this is information that this could correspond to what is true in the real world, but then what are you going to do with that? What predictions are you going to make? Who should get the high premium? Who should get the low premium? And that is not just a decision by the data scientist. That's like a well, political or a company or a business decision that has impact on how errors will be distributed on the two communities. So you can say, okay, and then all the males should get the high rate and all the females the low rate, but then all the false positives will be with the males, all the false negatives will be with the females. And this is, of course, a very extreme example, but in reality, this will happen like in 1,000 small profiles where the probabilities between males and females in risk is different, or where the proportion of males and females in these groups is different. And so I think it's not just a data problem. It's not just if you have better data, but also like disentangling these two things there. With the IRS also, it's probably not just a data problem. It's not that they were necessarily having a lot of biased data when learning the models, but it's also about the objective that they were optimizing. And I think this study is really showing a good way of like separating the things. There is the data science, so we need to learn models that are as good as possible and maybe have the red flags. And then it should be coupled back to the politics, and they should decide, yeah, but this objective is very important, and if it affects different communities differently, so be it. And if you don't agree, then next time vote for a different party. Or they could say, okay, this is really worrisome, and so we will target a different objective, but that's not a data scientist that needs to take this decision. If you take away the red flags, you also take that away. Then it's just accuracy that's being optimized, and just hope for the best.
Let's hope for the best. Okay, thank you, Toon.
You're welcome. Thank you.
So much.